Let's do another example where we have some data. We want to fit a line to that data and maybe use that to estimate some of the data that we didn't collect, so to speak. So the first thing they ask us, well, let's look at the chart first of all. This is birth year. They start at 1930. They go all the way up to the year 2000 in increments of 10 years. And they tell us the life expectancy in years. So a good thing for us, and I think this is the United States. The life expectancy has been steadily increasing. And the first thing they ask us to do is to make a scatter plot of the data. And I did this on Excel ahead of time, and this is what I got. As you can see, in 1930 it was 59.7. In 1930 it was 59.7. In 1940 it was 62.9. These blue dots are just plotting each of these data points. 1930 is 57.9. It's that data point right there. 1940, it was 62.9. It's that data point right there. So I just went ahead and plotted all of them. And then I let Excel figure out a line of best fit. And Excel, and I didn't go into the math of how to do this. We'll do that in future videos. That's out of the scope of an introductory algebra. But the Excel figured out that the line of best fit, the line that is least far away from all of these points, that minimizes the distance from all of these points, is y is equal to 0.2395x minus 400.99. And I'm not going to go into what r squared is just yet, but it's a measure of how good this line is actually fitting. So let's use that. Let's use this table. Let's use our line of best fit to answer the rest of their questions. So the second question is, use a line of best fit to estimate the life expectancy of a person born in 1955. So we have two options. We could just eyeball it. 1955 is right there. So if you go up from 1955, you're going to hit the line of best fit. Let me do it in a different color because that's the same color as the dots. In 1955, you're going to hit the line of best fit right there. And if I were to just eyeball it, it looks like it's right there. This is 1, 2, 3, 4, 5. So these are increments of 2. So it looks like about 77 years. So 1955, it looks roughly equal to 77. No, sorry, 67 years. Let me be clear. That sounded suspicious. A 67-year life expectancy. Now, we can use the equation of this line of best fit to come up with the exact value. When x is equal to 1955, what is y? What is the life expectancy in years? Let's get our calculator out for this. Actually, let me use a graphing calculator for this one right now. So let me clear this. Let me clear everything. And then let's just punch in 1955 for x. So we have 0.2395 times 1955, that's our x value, minus 400.99 is equal to 67.23. So our line of best fit gives us the exact answer of 67.23 years. So our eyeballing it wasn't that far off. So that's what our line of best fit would predict. If we assume that a linear model is a good model to describe this data, and all we know right now are linear models, so that's what we'll use. And it actually looks pretty good. It seems like it fits the data pretty good. Let's do the next part. Use linear interpolation to estimate the life expectancy of a person born in 1955. Now, linear interpolation means let's take the data points around 1955. So you have this data point from 1950. You have this data point from 1960. Let's draw a line between those two data points and assume that the 1955 number would be right in between on the line. Would be right in between on the line there. Now, we could figure out the equation of that line. We have 2 points. We have the 1950 data, and we have the 1960 data. We could figure out the slope of the line. We could figure out its y-intercept. Then we could substitute 1955 in there. But this is a line, and 1955 is right in between these 2 points. It's 5 from either one. So on this point right here, that's on that linear interpolation, on that orange, will just be halfway between these two. So we could even average those. So let's do that. So if we just average those, 68.2 plus 69.7 is equal. and then we want to divide it. That answer means our previous answer. So that number divided by 2 is equal to 68.95. So part 2, and through linear interpolation, we get 68.95. Is that what I got? 68.95. So that is this point right here. So linear interpolation is giving us, this is linear interpolation. I'll just write linear int. That's giving us a slightly higher estimate than our line of best fit across all of the data. And you can even eyeball it if you look at it right there. Let's do the next one. Use a line of best fit to estimate the life expectancy of a person born in 1976. Once again, we can use the equation of the line of best fit, plug in 1976 here, and see what it gets us. I mean, we can eyeball it. 1975 is there, 1976 is there. It'll be right around there. But let's actually use the actual equation. So in 1976, this is going to be the line of best fit. The line of best fit is going to give us, if we actually figure out what this line value gives us, so we get 0.2395 times 1976 minus 400.99. So 72.26 years. So it gives us 72.26 years. So equals 72.26. Let me make this clear here. These columns, this one right here is line of best fit, and this right here is interpolation. Now, they want us to use linear interpolation to estimate the life expectancy of a person born in 1976. So what they want us to do is draw a line between these 2 points, and then use that line, not the whole line of best fit, to figure out what 1976 might have been. Now, before, 1955 was right in between those 2 values. 1976 is not right in between those values. So let's actually figure out the equation of this line using the points, using these 2 points, using the points 1970, 70.8, and 1980, 73.7. Let's figure out the slope of that line, of this line right here. So the slope is the change in y over change in x. It's going to be 73.7 minus 70.8. 73.7 minus 70.8. That's how much we changed in the y direction, divided by how much we changed in the x direction. 1980 minus 1970. 1980 minus 1970. So this is going to be equal to, let's see, 3.7 minus 0.8 is 2.9. So it's 2.9 over 10, or it's equal to 0.29. We change 2.9 years in life expectancy every 10 years over that time period right there, or 0.29 per year. Now, what's the equation of that line? Well, we know that the point 1970 and 70.8 is on that line. So we know that when x is equal to, so if we say the equation is y is equal to mx plus b, we know that y is equal to, let's say 70.8. Y is equal to 70.8 when we know m is 0.29, when x is equal to, or when the year is equal to 1970 times 1970 plus b. Now we can calculate our y-intercept. So what is our y-intercept? Get our calculator out. If we have to subtract this from both sides. So b is equal to 70.8 minus 0.29 times 1970. Let's get our calculator out. Oh, there we go. All right. 70.8 minus 0.29 times 1970 is equal to minus 500.5. So this is equal to negative 500.5. So the equation of our interpolation line, remember, we're just finding the equation of this line between 1970 and 1980, is, that equation is y is equal to 0.29x, 0.29x minus 500.5. Now, if we want to figure out what that line, if we want to interpolate 1976, we just have to put 1976 in there for x. So what is life expectancy in 1976? Get our calculator out again. 0.29 times 1976 minus 500.5 is equal to 72.54. So we get 72.54 is what happens, is the number we get when we do linear interpolation between those two data points. All we did is we figured out the equation of the line between those 2 points, and then we plugged in the number 1976 to get 72.54. And that's a slightly higher number than what the line of best fit gave us. But it's pretty close in either scenario. Now, let's do this last part. Use the line of best fit to estimate the life expectancy of a person born in 2012. And this is what's cool about the line of best fit. We don't have 2012 here. 2012 goes off the table, but we could just keep continuing on with this line right here. Oh, I'm using the wrong color. Keep continuing with this line right here and see what does this line equal when the year is equal to 2012. So all we have to do is put 2012 in for x, and we'll get what the line of best fit tells us. Get the calculator out again. So we have 0.2395 times 2012 minus 400.99 is equal to 80.88. 80.88. So this last part, in 2012, if you were to use the line of best fit, the average life expectancy in the US will be 80.88 years. Anyway, hopefully you found that to be interesting. Sometimes dealing with the data can be a little bit hairy. These aren't nice, clean numbers, but it gives you a little sense of why slope and why intercept and interpolation and fitting a line is actually very important to analyzing data and coming to conclusions from that data.